So I just worked part A of example 1, and now I'm going to work part B. So part B is the question about, does the potential energy of the electron increase or decrease or stay the same when it's moved? Now I could just calculate this number. Now we know that the work that we calculated that had to be done on the electron was just equal to the change in the potential energy of the electron. So I calculate that number and figure out if it's positive or negative. But let me just sort of reason my way through this based on what we know about the electric field and the electric potential. So in terms of potential energy, if I move the electron against the field, the electron is actually, experiences a force by the field that points to the left. So if I were to just release the electron, it would accelerate to the left. So that means that if it moves in the direction that it would be accelerated by the field, its potential energy is going to decrease, right? Because if I just released it from rest, its kinetic energy would increase, and that would have to be coming from its potential energy, and so its potential energy must be decreasing. Now in terms of potential, I can answer that question like this. I know that if I move in the opposite direction of a field line, the electric potential is going to increase. And here I am moving in the opposite direction of a field line. I am moving from left to right. So the electric potential must increase as I move from point 1 to point 2. The electron is a negative charge, and the change in potential energy is the charge times the change in electric potential. And the potential increased, therefore the potential energy must decrease because the charge is negative. Right? So the potential energy of the electron is going to decrease as I move from from right to left. So from point 1 to point 2. The third part says that if we released the electron now from rest, so we moved it to this point here, that's point 2, and we release it from rest, how fast is it going to be moving when it is 2 centimeters away? So let's think about what that motion is going to look like first. So I now start out at point 2 and I release it from rest. What direction is it going to be accelerated? Well, it's going to be accelerated in the opposite direction of the field because the force that gets exerted on it is equal to the charge times the electric field, and it is a negative charge, so it's going to point in the opposite direction of the electric field. So this thing is going to be accelerated to the left, so it's going to take off to the left. And the question is, it starts off with a speed of 0. How fast is it going to be going after it moves a distance 2 centimeters? So let's just label this capital L. So if it travels some distance L, how fast is it going to be moving when it reaches that distance? So to answer this question, it's essentially a Physics 1 problem in terms of the method, and the method is conservation of energy. The only difference is that I have a new force that has a potential energy associated with it. So when I calculate the potential energy of the charge, I have to use the potential energy from this new force, and that's just the electric force. All right, so let's write down the let's write down the energy at the moment that it's released, and then the energy at the distance 2L away. So initially, initially the kinetic energy, the electron is at rest, so the kinetic energy is going to be 0. And its potential energy is going to be something. Actually, it doesn't really matter what it is, because we have the ability to say that the potential energy of the charge is 0 at any place that we want, just like we have the ability to set the gravitational potential energy for a mass to be 0 at any point that we want. So normally, if it's laying on the ground, we call this U is equal to 0, but we could offset that and call U equals 0 some distance h above the ground, and the reason that it doesn't ever matter is because it's the potential, or it's the change in that potential energy that's going to give us is the only thing that really matters in the physics of the problem. So let me just call this use of I right now. And then let me go to the point where it is, now let's look at the point that it has traveled 2 centimeters. So the thing's going to take off to the left. This is 2 centimeters, which I'm calling L. So this is the initial position, and this is the final position in terms of the conservation of energy that I'm trying to write down. Its kinetic energy is not going to be 0 anymore because it's going to have some speed. I don't know what that speed is, but I do know that whatever it is, it will have a kinetic energy that's 1/2 mv squared. Now this is an electron, so I know that the electron has some mass that I could look up. I'm just going to call that m subscript e to indicate that I know that it's a mass that's going to be some number that I can look up. And then the potential energy final. All right, so let me call that, oops, that's what I want to call it. The potential energy is UF. Now I don't know what those are yet, but basically what I'm going to do is I'm going to find that delta U is the only thing that matters, and I can actually calculate delta U. So the conservation of energy means, and I can use conservation of energy when I don't have any external forces, so I'm not applying an external force to the charge, it's only having a force exerted on it by the electric field. Conservation of energy says K initial plus U initial equals K final plus U final. So 0 plus U initial is equal to 1/2 mv squared. That's the mass of the electron, plus U final. And so here, let me solve for 1/2 mv squared. I've got U initial minus U final, which is actually equal to negative delta U, right? Because delta U is U final minus U initial. So really the only thing that matters is this delta U. It doesn't matter what the actual value for UI and UF is, because I'm going to subtract them, and all I want is that difference. Well, we've already calculated what the difference was between points 1 and 2 in part A, and so we're going to have the same thing here. All right, so I travel some distance L. My displacement in this case is going to be negative, right, because I'm moving to the left. So the displacement is negative L. The electric field is pointing in just the positive x direction. So this is a displacement that is exactly in the opposite direction of the field. So the change in electric potential is negative field strength times negative L, which is going to give me E times L, and that's positive, which makes sense because I'm moving against the electric field lines. So the change in electric potential is positive, but the change in electric potential energy of the electron is its charge times that, which means that its potential energy change is going to be negative, which makes sense. The potential energy has to decrease for the kinetic energy to increase if we're going to conserve energy, right? So I've got kinetic energy here, and I've got potential energy here. If the kinetic energy is going to go up, the potential energy has to go down by the same amount, right? Because added together, they have to give me the same number. So that means that 1/2 MeV squared is equal to this change in potential energy. And I need to be careful here because there's a negative sign here, and this is not that negative sign. Right, so there's a negative right there. The negative sign here came from the fact that the potential energy of the electron is decreasing, and then this negative sign came from the fact that when I did the algebra in the conservation of energy equation, that negative sign showed up. So those are going to cancel, which means that it's just going to be E, E, L. All right, so what I want is this velocity. I just need to solve for this velocity now. there we go. That's how fast it's going to be moving. So we can see that it clearly depends on the electric field strength, which makes sense. If the electric field strength was a larger number, then the velocity would be larger. So a stronger electric field is going to cause the electron to accelerate more. Let's see here. It depends on the length. So we're watching it, or we're looking at the speed after it travels 2 centimeters. If we waited and let it travel 4 centimeters, it'll be traveling faster because it will have accelerated for longer. Depends on the charge of the electron, which is of course a constant. But if we had some other negative charge that wasn't the electron, but had a larger charge than the electron, it would accelerate more over the same distance, and so it should be moving faster after the 2 centimeters. And then we've got the mass of the electron down here, and again, the mass of the electron is constant, but if we had another charge with a different mass, a heavier mass is not going to be accelerated as rapidly, and so it'll be traveling slower if we used a heavier mass. So that is the speed at a distance L. And the key here is that we can use conservation of energy, and we need to use the change in the potential energy of the particle to calculate what the change in the kinetic energy is, and from that we can calculate what the velocity is. But to get this change in potential energy, we have to first calculate what the change in electric potential is, and that's really why we use the electric potential.